In the last lecture, I introduced the idea of internal tension, internal shear force, and internal bending moment by calculating these things in a beam at a single point. So what we're going to do differently in this lecture is we're going to move from calculating these internal values at a single point to expressing them for every point in the beam at every point along the beam's length by drawing diagrams. So this time we'll expand on last lecture by expressing the internal tension, shear force, and bending moment at every point along the beam with diagrams. And so before I do any calculations, I'm just going to show you what this looks like. So for example, if this is your problem, you have a cantilever beam going to the right out of a fixed wall. Say it's 1 meter long, and at the right end you have a force vector of negative 800 newtons, positive 1,000 newtons. Then once you don't know how to do this yet, but if you draw the tension diagram, the shear force diagram, and the bending moment diagram for this beam, all of these diagrams are going to go from 0 meters, which represents this, to 1 meter along X, because remember for these beams we're always using a coordinate system like this. For this graph we're representing tension, for this graph we're representing shear force, and for this graph we're representing bending moment. And you would see, if you did this calculation, that the diagram for tension looks like this, where the value the whole way along is negative 800 newtons. The shear force the whole way along is negative 1,000 newtons. And the bending moment the whole way along is a line that should be straight. And I didn't write this, but so this is M. It starts at 1,000 Newton meters and goes down to 0 at the end point. Okay, so before I talk about how to calculate these diagrams, let's just all get on the same page as what this means. So what this means is that if you identify a single point along the beam, so say that you're interested in this point when x is equal to 0.75, okay, then go to x equals 0.75 on all of these graphs. And the corresponding value is negative 800 for the tension. Well, that's the same everywhere. The shear force is the same everywhere, negative 1,000. But at the bending moment, for the bending moment, we get a value of 250. And that's Newton meters. Okay, so that's how you use these diagrams. It's just a simple graph that represents the internal loads at every point along the length of the beam. Okay, so Now I'm going to give you the steps for calculating these diagrams, and I'm going to do it in terms of sort of an example problem. So here we have, on a fixed ground, we have a pin joint that connects this horizontal beam. It's a little messy. Sorry. Okay, so that's fixed there. And then halfway along the length, you have a little roller here. Okay, so this distance we'll make it 0.5 meters, and this distance will make 0.5 meters. And right at the end point, we have a load of 1,000 newtons. Okay? So this is the example. We want to calculate the internal loads all along the length, where we're going to use this coordinate system. And I'm going to use this example to illustrate the steps. So here's what you're going to do in every one of these problems. The first step, like the first step in most of the kinds of problems we'll do that you've done in statics and that we do in this class, you're going to isolate the whole beam. So before we make any cuts, we're going to isolate the entire thing, and we're going to find the reactions. And I'm going to do this, I'm going to go through this problem completely at the end. Right now I'm just going to use this as a quick reference to show what I'm talking about. But if we're going to calculate the reactions of this beam, there's going to be a force vector at the pin joint, and then there's going to be a vertical force, vertical force acting at the midpoint. The second step, once you've found those reaction forces, is to identify the x values at all important points. Okay, that's what I'm going to call these, important points. These are points where things change. And these important points include ends of the beam. They include any locations of point forces or point couples. And they also include, we haven't talked about distributed loads yet, but we'll talk about that in the next lecture. And they include the points where you have changes in distributed loads. So for our example up here, what are the important points? Well, there's one at x equals 0, because that's the first endpoint going from left to right. There's one at x equals 0.5, because you have a point load acting there. Okay? Yeah, you also have a force vector acting at this point, but that's the same as the end, so that's 0 in using both of those criteria. And then you have a point load acting at the end point, and since it's also the end point, you would treat it anyways. So we have 3 important points in this example problem, and those points are going to be sort of key cutoffs in where we choose to draw our cuts. So now going on to step 3, you'll make a cut, and I'll explain what that means. Between each adjacent pair of important points. Okay, so for us, we're going to make a cut that falls somewhere between 0 and 0.5, and we're going to make a cut somewhere between 0.5 and 1. Okay? So we're going to have two cuts in our problem. For each of these cuts, we'll define a variable x that can represent any point in that region between those two important points. Okay, so let's go back here and look at what I'm talking about. So if our important points are here, here, and here, right, then we're going to have cuts that represent this region and this region. And for each of these cuts, we're going to have our variable x represent every point from this side of the left, from the right side of the left line to the left side of the right line. Okay, so everything up to, but not including, our important points. Okay, so let me illustrate that here. For our first cut, using our example, our region will go, like our free body for that we're going to use Newton's second law and the rotational Newton's second law for, is going to go from 0 on the left to some value of x on the right. And x is any value, it has to be able to represent any value between 0 and 0.5. Okay? Then for the second cut, we're going to, as our free body, go from our 0 to an x that's between 0.5 and 1. Okay? And what does that mean? It means that in our first cut, what loads do we have? We'll have our reaction load there, and here we're going to have tension, shear force, and bending moment. And for our second cut, we're going to have the reaction force. We're also going to have our force at, say, this is the point B, due to that roller. And then we're going to have, again, a tension, a shear force, and a bending moment. And what we're going to do in both of these cases is solve for these three internal loads, given the rest of the loads, and treating our cut as our free body. For each cut, then, we're going to use Newton's second law and rotational Newton's second law to calculate our internal loads, T, V, and M, as functions of x. Now you're going to see that I always start at the left and work to the right, but you don't have to do that. You can start at the right and work to the left. You just have to use the sign convention that I described in the last lecture. Okay, so instead of drawing your tension and your shear force and your bending moment this way, if you're moving this direction, you're going to have a tension this way, a shear force this way, and a bending moment this way. Okay. Okay, so let's do an example problem And let's do the one that I've already given you, that I drew right at the top of our problem. So step 1, we're going to isolate the whole body, and I'll call this reaction force, I guess I'll call it RA. We know that we have also a reaction RB that's vertical, and we have a 1,000 Newton force downward acting at the right end point. So Newton's second law says RAX, RAY plus 0 RB plus 0 negative 1,000 is equal to 0, 0. So right away we know RA is 0, but we can't solve this one yet. So now we'll go to the rotational version of Newton's second law, and let's do it about the point A. So what do we have? This force, RB, would produce a counterclockwise moment of 0.5 RB. Then we'd have a clockwise moment of 1,000. So solving this system of equations, we get that RB is equal to 2,000, and RA is equal to 0, negative 1,000. So now we know all our reactions. So now we're moving on to our step 2. And that is identifying the important points, which I already did. For this example problem, I already did. So X is the X value where the important points lie are 0, 0.5, where the point force is, and then 1.0, where the other point force is and the end is. So that means our cuts are going to be defined by X between 0 and 0.5. And our second cut is going to be defined by X somewhere between 0.5 and 1. Okay. Now we move on to step 3. And we're going to look at these cuts individually. So our first cut, it goes all the way from the left, where X is equal to 0, to a right end point of X, where X lies somewhere between, and just so we're on the same page, this is cut 1. So X is somewhere between 0 and 0.5. Okay, so what loads are acting on this piece? Well, we're going all the way from 0, so that left reaction force, RA, which we calculated, let's see, 0, negative 1,000 is acting. And then since X can't include 0.5, we're definitely not going to have that point load. So the only other loads acting are the tension, the shear force, and the bending moment. Newton's second law for this piece says 0, negative 1,000 plus T, 0, plus 0, negative V. And why is V negative? Because we have our arrow drawn downward. So if you have a positive value of V, it means that we're going to have a negative Y value for this vector, right? So this is the vector that represents that. So we can see that T is going to be equal to 0, and V is going to be equal to negative 1,000. And now look at the rotational Newton's second law, and we'll calculate it about the point A all the way at the end here. So what moments are acting about this point A? Well, this reaction force doesn't produce a moment, but V does, and if V is positive, we'll have a clockwise moment about A, which is negative, so we have a moment of negative Vx. The tension won't produce a moment because it goes right through this point A that we're looking at. So the only other thing we have is the bending moment. That's a couple, so no matter where it's acting, no matter what point you're calculating the moment about, that coupled, you just add on. Well, V is negative 1,000, so we have here m equals Vx, so m is equal to negative 1,000x. Okay? And these equations hold for x between 0 and 0.5. We only have one more cut left to do. Oops. And that cut starts all the way at the left, and this time the right ends anywhere between 0.5 and 1. So we still are at 0 here, we're still at x here, but x this time has to represent something between 0.5 and 1.0. And it's non-inclusive of the endpoints, so it can't include 0.5 and it can't include 1, okay? So that means we're not going to have that downward force of 1,000 acting here, but we definitely are going to have this upward force, RB, that we calculated as 2,000 newtons. And we're definitely going to have the reaction force at this endpoint of 0, negative 1,000. What other loads are acting? The tension, shear force, and bending moment. So Newton's second law says 0, negative 1,000 plus 0, positive 2,000 plus T0 plus 0, negative V is equal to 0, 0. So right away we can see again that T is equal to 0 and V is equal to, last time it was negative 1,000, this time V is equal to positive 1,000. And now we'll use the rotational Newton's second law about A. This is what I always do. I just always use that left point to calculate my moments about. I'm always in favor of developing a method, sticking with it every time. It's just systematic. It keeps you from making errors. So that's what I would recommend you do. But you don't have to make that, you don't have to calculate your moments about the same point every time. Okay, so what moments are acting? Well, this reaction force won't produce a moment about A, but this force of 2,000 newtons will. It'll produce a counterclockwise moment of 0.5 times 2,000, so plus 1,000. And then we're still going to have a clockwise moment produced by V, and that's acting at a distance of x from A, so we're still going to have minus Vx, and you'll always see that minus Vx in there. Then we'll have a moment produced by this couple, the bending moment. The tension T, again, goes right through that point A, so it doesn't do anything. We know what V is, so M is equal to 1,000x minus 1,000. And these equations, which are different than the other ones, so at first glance you might sort of wonder what's going on. Like, is that possible to get different values? Yeah, because these hold for totally different regions of the beam. These equations hold for x between 0.5 and 1.0. Okay, so now we're going to draw the diagrams. So here's our tension diagram. And it goes from x equals 0 to x equals 0.5 to x equals 1. The tension's pretty about as simple as you can get. The shear force here, we're also going to have 0.5 and 1. And this is x, and then the bending moment. Okay, so what do these diagrams look like? Well, for x between 0 and 0.5, the tension is 0. And for x between 0.5 and 1, the tension is 0. So the whole way along the beam, there's no tension, which makes sense because there were no horizontal forces applied to it. Now let's look at the shear force. For x between 0 and 0.5, we have a shear force of negative 1,000. Then when we get to 0.5, we have a jump in the shear force. It jumps to positive 1,000. So we start out at negative 1,000 and then jump to positive 1,000. And notice, this is something that always happens. This jump in shear force corresponds exactly to the point force that acts at this point. There was a 2,000 Newton point force acting at x equals 0.5, and that's why you have this 2,000 Newton jump. And now the bending moment. For x between 0 and 0.5, we have a bending moment that it's linear, and it starts at 0, x is equal to 0, and it ends at x equals negative 500. And then for x between 0.5 and 1, it's linear again, and we'll start at negative 500 and we'll end at 0. And these diagrams are going to give us really useful information about where to look at an object for likely problems, breaks and plasticity and whatever else can go wrong. If you expect this member to be especially susceptible to breaking due to bending, then this is the point that we're going to worry about. This x equals 0.5, halfway through the bar. So this tells where the beam is most likely to break. And here's some stuff that you should keep in mind. Okay, these are things that will always happen with every set of internal load diagrams that you draw. First, you'll have discontinuities in tension at the location of horizontal point forces. We didn't have any of those in this example, but we had a vertical one, and you saw the corresponding fact for shear forces. So that's the second thing to keep in mind. Discontinuities in the shear force occur at vertical point forces. And third, discontinuities in the bending moment occur at point couples. So one consequence of this third thing to keep in mind, a consequence of 3 is if there's no point couple at the end of a beam, the bending moment should be 0 there. Okay, so that's one way to sort of check your work that ends up being pretty useful. Where do you have point couples? Well, sometimes they're given to you explicitly. It says apply a couple here. But a lot of times point couples occur because of fixed joints. So if you have a beam that's free at one end, it's not connected to a wall by a fixed joint, and there's no couple drawn on it, then you know that the bending moment should be 0 there. And if it's not, you made a mistake somewhere. Okay, so now let me give you a practice problem to work on. So say that you have a wall. This time it's on the right, and you have a beam connected by a pin joint, and it's connected at the midpoint by a cable. And let's say that these distances are 0.25 meters. And at the end of the beam, whoa, yikes, you have a vertical force of 5,000 newtons. Draw the tension, shear force, and bending moment diagrams. And let me just say, just because this beam is connected at the right doesn't mean that you have to go from the right. You can actually still go from the left in this problem, and that's what I would recommend. But if you want to try going from the right, I'd say go for it. I think that can only help your understanding. So please let me know if you have any questions, and I'll talk to you soon.